Now moving on to part B, we want to find the expected value of x. So to find the expected value of x, by definition, this is just equal to the integral of x multiplied by the probability density function. So all we have to do is to substitute this expression inside the integral. So we have x times a times e to the power of negative lambda x minus a squared dx. And then what I'm going to do now is something similar to what I did before. I'm going to apply the substitution u equals to x minus a. So if you remember from the last video, applying this substitution doesn't change the bounds, so we have negative to positive infinity, and then we have capital A, and then for x this just becomes u plus a, so we have u plus small a, and then here we have e to the power of negative lambda times x minus a squared, and x minus a is just u, so this just becomes u squared, so I don't even need the bracket, so this just becomes u squared. And then for this substitution, du is equal to dx, so I can just substitute dx with du. So now the challenge becomes evaluating this integral. So I'm going to break apart this bracket here and then separate this expression into two separate integrals. So now we have a times the integral u times e to the power of negative lambda u squared du, and then we also have, I'm going to pull out the small a, and then we have this integral. I'm going to put the big A back inside the integral, because you can see that if I put the big A back inside the integral, this expression is really just integrating. So this is just integrating the probability density function. And by definition, this integral is equal to 1. So we know that this expression is just equal to 1. So for this entire expression, we have 1 multiplied by small a. And so now all we have to do is to evaluate this expression. So the challenge we face now is evaluating this integral. So all we need to do now is to evaluate this integral. And it turns out this integral is actually equal to 0, because this expression here is actually an odd function. Now an odd function is a function that satisfies this property. So f of x is equal to a negative of f of negative x. So a function, an example I can give you on the top of my head at this moment is f of x is equal to x to the power of 3. And if you graph this function, you can see that it will look something like this. So you can see that for the function for the half in the negative x-axis, you can see that this is really just a 180-degree rotation of this section over here. And for an odd function, if you integrate it from negative to positive a, you will always get 0, because first of all, if you integrate it from negative a to 0, you're adding up all these negative contributions, so you have all these negative area. And then when you integrate it from 0 to positive a, you have all these positive contributions. And then if you add them up, they'll just cancel each other out. So in the end, you'll just get 0. And then for this expression here, this is precisely an odd function. And so that's why if we integrate this from negative to positive infinity, we will get 0. So this expression here is just 0. So in the end, we have 0 plus, don't forget the small a, and then multiplied by 1. So it's just equal to a. So the expected value of x is just equal to a. And so that is the expected value. Now the next thing we want to find is the expected value of x squared. And now by definition, this is just equal to the integral of x squared multiplied by the probability density function. So we just go through a similar process. So we substitute in the expression for the probability density function, and then I'll apply the same substitution. So once again, the bounds don't really change. We have capital A, x squared just becomes u plus a squared, and then this e term becomes e to the power of negative lambda u squared, and then dx just becomes du. And then expanding this term, we have, so this integral is equal to, so we have a times u squared plus 2au plus a squared, and then we also have e to the power of negative lambda u squared du. And then I'll just separate this expression into 3 separate terms, and we can evaluate them separately. So first we have capital A multiplied by, first of all, u squared times the e term, and then we have 2a multiplied by a times u e to the power of negative u squared du. So you see, once again, we have this odd function appearing as before, so we already know that this is equal to 0. And then finally, for the third term, we have a squared multiplied by the integral from negative to positive infinity, And then we have capital A times e to the power of negative lambda u squared du. So we already know this term is equal to 0, and then we've also encountered this term before. Remember I told you that this term is really just identical to the integral of the probability density function, which by definition should be equal to 1. So it turns out that this expression here is equal to 1. So in the end we have this expression, which is equal to 0, so this is equal to 0, so we can just ignore this. And then now we have 1 times a squared, and then now we have this third term here, which we haven't evaluated yet. So now the challenge remains for us to evaluate this integral. And so at this point what we want to do is to evaluate this integral. So this is just the integral given over here. And in order to evaluate this integral, we're going to use the integral that I invoked in the previous video. Remember in the previous video I told you that this integral is equal to the square root of pi divided by lambda. I didn't prove this result. I told you you can arrive at this result using double integrals, but I just used this result directly. And for evaluating this integral, I'm also going to use this result directly without proving it. So how can we use this result to arrive at the value of this integral? And the trick is to differentiate both sides with respect to lambda. And when you differentiate both sides with respect to lambda, for the left-hand side, you can see that this is an integral with respect to u, so I can just differentiate the term inside the integral directly. So differentiating this e term, I will be treating lambda as the variable, so negative u squared is just a constant, so we have negative u squared e to the power of negative lambda u squared du. And on the right-hand side, we have the derivative of square root of pi times lambda to the power of negative 1/2. So the right hand side just becomes square root of pi, negative 1/2, lambda to the power of negative 3/2. And then you can see that these negative signs cancel out. And on the left hand side, this is precisely the expression that we want to evaluate. And this tells us that this expression is just equal to, first of all, 1/2. And then we have lambda to the power of negative 3/2, so that's just equal to 1 over lambda times 1 over square root of lambda. And also don't forget our square root of pi. So to write this in a nicer way, we have 1 over 2 lambda times square root of pi over lambda. And so that's how we can evaluate this integral. And so now going back to this expression, now we know that this expression is equal to 1 over 2 lambda and then square root of pi over lambda. And so now we're ready to finalize our result. So remember, what we're looking for is the expected value of x squared, and then now we know that the expected value of x squared is equal to capital A, which we found in the last video is just equal to square root of lambda divided by pi, and then we have 1 over 2 lambda and then square root of pi divided by lambda, and then plus, and then we have 2a times 0, so we have plus 0, and then here we have a squared times 1, so plus a squared times 1. And then you can see that these terms conveniently cancel out, so in the end we have a squared plus 1 over 2 lambda. And there you have it. This is the expected value of x squared. And so we have found the expected value of x squared. Now finally, what we want to find is the standard deviation of the probability density function. And in order to find the standard deviation of this distribution, what we have to do is to evaluate the variance first. So the variance is just the standard deviation square, and by definition this is equal to the expected value of x squared minus the expected value of x and then squared. And we have just found the values of both of these expressions. So first of all, we have the expected value of x squared, which is just a squared plus 1 over 2 lambda. So this is what we just found. And then the expected value of x, we found that this is just equal to a. And so therefore we have minus a and then squared. So these two conveniently cancel out. So in the end we have 1 over 2 lambda. And so the standard deviation is just a square root. So there we have it. This is the standard deviation of the distribution. And so in part C, we're asked to graph the probability density function. So let's do just that. So we have the probability density function. And then you can plug in something into your computer that looks something like this, and you can see the overall shape of what this probability density function should look like. So I'll just give you a rough idea. So I'll just assume small a is positive, And if small a is positive, your probability density function should look something like this. So it should be a symmetrical curve that looks something like this. And this very point where it hits the peak, this should be the point where x is equal to a. And so this is what your function should look like. And as you might have guessed, integrating this function from negative to positive infinity should be equal to 1. So the area under the curve is precisely 1. And so this is a rough idea of what your probability density function looks like.